Okay, so got a molecule here, we drew it here. How many proton and carbon NMR signals would you expect? Label them and include predicted frequencies. So this is just using your tables, but also looking for symmetry in this molecule. So this molecule does have symmetry. If you cut it in half this way, it's the same on either side. So because of that, it has less different peaks than you'd expect. So in the proton version, you look in here, you have 4 types. So these sets of this 4 are the same. These 2 D's are the same, B and A, so 4 types. The frequencies, just using the table again. 4, 4.5. I just said it would be a little higher because it has both. It's both allylic and next to the oxygen. B is a little higher. C is just saturated, and then D is that vinyl, 4.5 to 6.5. Same with the carbon. Again, not as many as you expect because of symmetry. So 1, 2, 3, 4. And the frequencies, just again using the table, 100, 100 to 150 to 50, 0 to 50, 150. So just using those tables to be able to identify those positions. Okay, so circle the molecule that's represented by the IR spectrum and explain how you eliminate it. So the first thing I did, I started looking at the numbers and predict what they mean. You see these sharp peaks down here around 30,000. If it's above 3,000, that's sp2ch. If it's just below 3,000, it's sp3ch. Peak around 2,200 means either nitrile or triple bond. The peak in this area means carbonyl, right? That's a aceto-bondo stretch. I don't know which type yet, but it's aceto-bondo stretch. And then these two really tell me it's a benzene ring. So if you look at that table, one of those tables, it has benzene rings have 2 stretches here, but that's kind of guessing at this point. So I'm not absolutely sure that's a benzene ring. The reason why I think it might be also though is because this sp2ch is right at that spot where it says aromatic or benzene. Those mean the same thing. Those sp2chs. So that maybe helps me think it has a benzene ring there. But again, you're not absolutely sure yet. But if we go here, let's start eliminating possibilities. So it wasn't A because A doesn't have a triple bond. So it's not A. It's not B because there's no sp2chs, right? I have that sp2ch up here. This has only sp3chs, right? No sp2s. It's not C because I don't have a OH stretch. Well, it is D, but it's not E. Why is it not E? Because E doesn't have any, well, it should also have an NH2. There is no NH2. It also doesn't have any sp3chs, right? And my RIR here up here had sp3chs. And if it was E, you'd have to have NH2s, and you'd also have to have that SPCH, but that's missing. So those things are missing, so it has to be D, because D has a triple bond, has a carbonyl, has sp3chs and sp2, and it has a benzene ring. So that's what the best answer is. But that's what I'm looking for, process elimination. So what is distinctive about IR stretches between a terminal alkyne and internal alkyne? So this kind of comes back to remembering when we talk about sp3, sp2, sp CHs or alkene, alkyne CHs. So the only difference, right? The difference is the number of pi bonds they have. That also affects the length of those bonds. So that affects they have different IR stretches because of that, right? So those all have different numbers, right? So SPCH is around 3,300, SP2 CHs are just above 3,000, and then SP3 are just below around 2,900. How do I tell the difference between internal and terminal? How do I tell these apart? Is really based on whether or not there's a hydrogen, right? Internal alkynes don't have any carbon-hydrogen bonds. There's no SPCHs, whereas terminal ones do have SPCHs. So that's the way you tell them apart. Now these ones are these alkenes. This is right from your table, right? So I didn't put this in there. Table has the answers, right? So it's a matter of identifying those things and being able to say, okay, right, this is a tri-substituted, this is a di-substituted trans, this is a di-substituted terminal, right? This is a mono-substituted, and this is a di-substituted cis, right? So there's numbers that are associated with those just based on the IR stretches. So that's the one time you would use the fingerprint region. That's what those are for here. So let's see. 2 molecules. How many hydrogen, how many carbon signals do you expect? Label them. So these molecules are not very symmetrical, right? So there's no mirror. So everything ends up being different, right? A lot of people get confused, like, how are A different than B? Well, A and B are the same distance from OH, but this A is closer to this oxygen than this and this. So, right, there's no pure symmetry. So there's 6 types. 1, 2, 3, 4, 5. And then don't forget the OH, 6. Carbon, same deal. There'll be 10 types. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Again, not very symmetrical. It'd all be different peaks in the proton, or in the carbon NMR, and also in the proton NMR. Another NMR problem, again, asking you for the number of signals, but also asking for integration this time, and the frequencies. So there's some symmetry up here in this part because you can rotate about the single bond. So A is on both sides here, right? And B is on both sides, and then there's C, D, and E. So A is worth 6 hydrogens because there's both these CH3s. B is worth 4 because both those CH2s. C is worth 1. D and E. And then frequencies, these are saturated, so 0 to 1.5. Same with B. C is allylic, so that's that allylic region. And then D and E are both in the vinyl region, so they're a little higher up, a little more D-shielded. There you go. So in this one, I'll give you the steps. All right, it's acidic conditions, H+. Why don't you add all the lone pairs? Maybe I forgot to do that. You should do that if I tell you to. Label bonds broken and bonds formed from the start material. All right. So what I did here, all I really wanted was from here to here. So bonds formed was C2 to O3. All right. So this is C2, O3, and then S1, H4. Those are the bonds formed and broken. That's all I was really looking for there. I wasn't looking for like every step of the way doing it. I just wanted you to do it from here to here, just to show what's going on there. First step, protonation. Right, makes this a more reactive electrophile. Carbon of the carbonyl group adds to there. Right, breaks the pi bond. Get a tetrahedral intermediate. We're going to need to do a proton transfer to make this a better leaving group. Remember, we're in acidic conditions, so it should have no minus charges. Acidic, no minus. Makes this a better leaving group. Electrons come down, kicks that out. Makes the sulfur. Then we do a final proton transfer to regenerate the catalyst. Acidic conditions. Proton transfer, we're going to make this a better leaving group. We're going to make this more reactive. Things are going to add. All right, we're going to break the pi bond. Balancing our charges, this oxygen has a plus charge. All right. We're going to do a proton transfer, make the nitrogen a better leaving group. Electrons come down, elimination. Intramolecular addition, breaks the pi bond. Balancing our charges, plus charge there. Proton transfer at the end, regenerate the catalyst. All right, last one. Here, steps, addition, proton transfer, elimination, proton transfer. So there's no charges in this one. There's no H+ or a negatively charged nucleophile. So this is a neutral condition reaction. Right? So the first step is addition. We have a negatively charged oxygen here. Again, similar to the quiz, we need to do a proton transfer. This is the most reactive piece. O- needs to do a proton transfer. Go from no charges to charges. Now from here you do elimination. You're going to get charges again. O- H there. That's our final proton transfer to get to the two products. So neutral conditions, you need to go from no charges to charges, back to no charges, back to again. So a good point of clarification, because this anhydride is symmetrical, it doesn't matter which carbon you go for, because you get the same product either way. All right, the last one. Give the mechanisms. Both steps are just addition, elimination. So I did the mechanisms for each. Add, eliminate. These are basic conditions, all minus. Add, eliminate, get to the two possible products. And then which is more reactive, A or B? Explain why. So A is more reactive because it's not doing resonance. It's not able to do resonance. So that leaves this lone pair more available to react. And then which product is more likely, C or D? So C is more likely because it's more stable. Right, it has the worst leaving group. Right, it's lower on the Mount carbonyl than the anhydride is. It also comes from the most reactive starting material. Right, so it's making the most stable product. So that's kind of what I was looking for there, right? The kind of remember thinking about reactive starting materials and stable products and how those things affect reactions.